Hi students, Professor Nugent here. In this video we are going to continue our discussion of the maximum likelihood estimator. We're going to focus on the probit case and we'll take a look at the logit case as well. The derivation of the probit likelihood with one independent regressor starts with the density of the first observation of y given x. Okay, so we're starting with the first observation of y given x. Recall that the left-hand side variable is in essence the probability that y equals 1 given x. So we're thinking about the probability that a mortgage is denied given the applicant's demographic characteristics, the home value to loan ratio, things like that. Or we can think about the probability that a country uses a capital control given the monetary conditions. That is what we're thinking about. So here we have the probability that y1 equals 1 given x1, and that's equal to the cumulative standard normal distribution function of beta naught plus beta 1 times x1. We have two outcomes, right? We can have the probability that y equals 1 and the probability that y equals 0 given x1, and that's the complement. So we have line 1, line 2 is the complement to line 1, so that's 1 minus the cumulative standard normal distribution function of beta naught plus beta 1 times x. So the joint density, that's not the joint density. The density, the general form of the density that y1 equals little y given x is the product of these things to the power of little y. And when little y is equal to 1, then the second term will drop out. When little y is equal to 0, the first term will drop out. Just like we saw in the last video. The probit likelihood function is the joint density of y1 through yn given x1 through xn treated as a function of beta naught and beta 1. So these words mean the probability that the joint probability that the different observations of y1 through yn equal to little y1 to yn given the values of the independent variables, and that joint likelihood is a function of the values of the probit coefficients. So this joint likelihood that the different observations on y1 through yn equal to 1 or 0 is a function of beta naught and beta 1 given the values of the independent variables x1 through xn is equal to, as we saw in the previous video, the product of their densities for y1 through yn. And so here you have the density for the first observation, and this is multiplied all the way through the density for the last observation. Our maximum likelihood estimators of beta naught and beta 1 maximize this likelihood function. Now we can't solve for this maximum explicitly, so the maximum likelihood estimator is maximized using numerical methods which is what is happening when you see the iterations occurring in state type. As in the case of no independent variables, no regressors on the right hand side in large samples, the beta naught, the coefficient on the constant regressor, and beta 1 hat, they are consistent, they are normally distributed, and they're asymptotically efficient among all efficient estimators, assuming the probit model is the correct model. The standard errors are computed automatically using stata. Testing confidence intervals proceeds as usual, and this extends to multiple independent variables. You'll use the Z statistic, the normal distribution for a hypothesis test, for one coefficient, for multiple you should use the F chi-squared Q over Q. And you'll see the chi-squared statistics given as well in the stata output. The only difference between probit and logit is the functional form used for the probability. The cumulative normal distribution function is replaced by the cumulative logistic function. Otherwise, the likelihood is similar. And for details, you can check out the appendix. As with probit, the maximum likelihood estimators for logit, they are consistent, they are normally distributed, their standard errors can be computed, and testing confidence intervals proceeds as usual. Let's take a moment to look at measures of fit for logit and probit. The R squared and adjusted R squared that we compute using OLS, they don't make sense here. Now, why not? Well, recall that R squared and adjusted R squared refer to the sample variance in Y explained by the variance in X. But we're not seeing variance in Y because there are only two potential values for Y. So we need some specialized measures to think about the measures of fit. The first is the fraction correctly predicted. This is the fraction of the y's for which the predicted probability is greater than 50% when y is equal to 1, or is less than 50% when y is equal to 0. The next is pseudo R squared, which is more commonly used, which measures the improvement in the value of the log likelihood relative to having no independent variables. The pseudo R squared simplifies to R squared in the linear model with normally distributed errors. This is all the content that we will cover in chapter 11. Stay tuned to the next video in which we will think about the application of the Home Mortgage Disclosure Act in more detail.